So I've been wanting to make a game for a while now, and I figured that starting a YouTube series would be a great way to help keep me motivated and on track. One of my long-term goals with this channel is to eventually write my own engine. It's something I've wanted to do since I was a child, and I've been learning a lot about the process since I started playing around with this idea. I'm going to be keeping that in mind as I build this project, and I'm going to be trying to abstract what I can out into the engine layer as I go. I eventually want to build several games over the course of this series, and each one will contribute to the engine in its own way. I've always wanted to build a roguelite. The main advantage of building a roguelite is the sheer amount of variation that's available. Everyone can have a different experience, and that variation can come with a low development cost. With the architecture I'm planning on using, it should be fairly easy to create a large variety of elements that will influence a run, such as buffs, debuffs, weapons, and more. I'm going to be using procedural generation to make sure every run is a little bit different. My map system is modeled after Slay the Spire, and my reward and loot systems are based on a combination of that game and The Binding of Isaac. I was thinking that a shoot-'em-up would be fun for the main gameplay. I'm taking inspiration from Enter the Gundam, but I've only played about an hour of that game, so I really don't know how much of an influence it's going to have. I really like using an entity component system style of architecture for my games. Here's a quick breakdown of how that works. Everything in the game world is represented by an entity. Players are entities, background tiles are entities, bullets are entities, UI elements are entities. I think you get the picture. An entity is simply a unique identifier, which in this case is going to be a 32-bit integer. Since everything is just a 4-byte value, that means that we can have a lot of entities in the game world and still maintain high performance. In a normal object-oriented approach, components would simply be members of an entity object. In this system, we build entities from sets of components. This distinction might not make complete sense now, but it'll become more clear once I start implementing this. Using this data-oriented approach will allow us to create pools of component data, which can be looked up with an entity identifier. This system will help avoid cache misses, which can really impact performance. This also means that we can be a lot more dynamic with our game, since an entity can have any component assigned to it at runtime. If a player steps in hot lava, a lava component can be created and attached to that player. If an enemy is hit with a cursed weapon, that cursed component can be created and attached to the enemy. In short, components will improve development speed and game performance. The final element in the ECS architecture are systems. That's right, this isn't an entity component system. This is entity component system architecture. Systems can really just be thought of as functions or methods, and they're analogous to the control layer in the more familiar model view control architecture. Every time the game updates, each system is called and updated with a time delta from the last update and a reference to the world object. Physics, audio, input, event handling, rendering, and anything else that a game can do is handled by a system. The key advantage of using systems is that they simultaneously offer a way to decouple code, and they strongly encourage decoupling code. I found it much more difficult to write spaghetti code when using an ECS than writing good, clean, decoupled code. The dependencies I'm going to be using for this project are SDL2 and Entity. SDL2 is a cross-platform library that will help create a window, handle input, incorporate audio, and it will eventually be used to incorporate OpenGL for 3D rendering. Entity is the framework I'll be using to implement my ECS. One thing to keep in mind is that it's written in C++17. If you're following along at home, make sure your compiler is set to use at least C++17. So I wanted to demonstrate what I've come up with so far. I create a game object, and just very simply we start it, and then once it's done running, we call the destructor with the delete operator. Very simple main function. Now when we get into the game object, this is where things get a lot more tricky. You can see we have a world registry We have an array of systems, and right now an array of empty systems. I think this might change in the future. It's not the best solution, but basically as we add and remove systems, there's going to be holes in this array, and we can fill it by remembering which positions those are within empty systems. Right here we've got pointers to our input and window managers. And then there are private functions that run the game loop, initialize systems, and register quit events. And then here you can see the public constructor and destructor, which are called right at the beginning and end of main, as well as start, and then a stop function that's going to be used elsewhere. There are also functions to add and remove systems. I decided to make these part of the public API just in case I want to add systems from elsewhere at some other point. Coming into this C++ for the game object, you can see we initialize SDL, create a new registry for our world object, and then initialize the systems and register quit events. Here's how systems are initialized. We just create new systems. Each of these derives from the system class, which is just a really simple base class. Mainly it's got a constructor, a destructor, and this virtual update function that every system needs to include. Back in our game object, initializing systems, we create those two system pointers and then add them to our current system array. Here in the register quit function, we create a reference to the stop function, which is bound to this current game object. And then we register event with the input manager. We're registering the SDL quit event, and we should call the stop function as the callback function. And then right here are our key events. We need to specify SDL does not have just an alt button, so we need to specify the key combos for left alt and right alt, as well as F4. The same thing goes for control and W. For each of those, we just pass in the stop function as the callback function. The stop function very simply just sets running to false. Start sets running to true and kicks off our game loop. Within the game loop, we start by getting the current ticks. We set the current ticks to the previous ticks, and then we enter the loop. Every time we go through the loop, we get the current SDL ticks. We loop through every system and update it with the current minus previous ticks. That's going to be our delta, and pass it a reference to the world object. And then we set the previous value, the previous timestamp, to the current timestamp once we're done updating everything. Coming over to the WindowManager class, you can see we have a window reference and a renderer reference. These are going to be important for actually rendering to the screen. And then we have a uint32 that stores the amount of ticks since the last update. We don't want to render on every single update, as it can lead to slowdown in our system. So instead, we just want to update whenever it's necessary. We calculate that with the ticks per frame macro, which uses the target frame per second, which at the moment is set to 60. This is really easy to modify though. We also have a render function as well as the 3 public functions inherited from the system class. As you can see, when we call the constructor, we're initializing the video subsystem within SDL. We create a window with the title of SHMUP. We center the window on the screen. Right now we're setting it to 640 by 480, but as you can see, I have plans to abstract that later. I think it's going to go in a config file. And then right here are our window flags. Right now I have no flags enabled. This right here is where we'll do OpenGL enabling later. We also come down and create a renderer and just plug that into the window. We have to give it a reference to the window, and then we set it to hardware accelerated mode. The window destructor, when we're done using the window, we just destroy the renderer in the window. And then every time we update, you can see we add to that ticks counter. If the ticks is greater than or equal to the frames per tick, or ticks per frame rather, then we're going to subtract that ticks per frame from our current ticks and then go ahead and render. Right now the render function is simply sets the renderer draw color to black. This is red, green, blue, and then alpha. Alpha is just the transparency, so we want it fully visible. We call render clear and then render present. In between these two functions is where we would render anything else that we have, although we have nothing to render right now. So now we're coming over to the InputManager, which was a really fun class to implement. Right here we've got a keys object. This is a map that maps scan codes, which are the keys currently pressed, with a true or false value. This is going to keep in every single update. It's just going to keep an event of which keys are currently pressed. We can go through and check which key events are registered, and if any of these are activated, then we can go ahead and call the callback function. These are just more maps to scan code. This has a vector of scan code, so you can have key combinations like Alt and F4, and then this one just takes an event type. This would be like our SDL quit event. In both the cases, they just take a void function. Over here, you can see we actually don't do anything on construction and destruction of the input manager. On the update function, we create an SDL event and just continue polling events until the SDL event stack is cleared. And then we pass each of those events to update keys and update events, which just check which keys are pressed or if there's a current event happening. And then we also update our key events. So when we update our keys, we just check, is the event type a key down or a key up? If so, we call on key down or on key up. Each of these just takes the map, the keys map, and it says, okay, whichever scan code is currently pressed, that is true. Or whichever scan code was currently lifted, we'll set that to false. When we update our key events, we just loop through our key events function, through our key events map, and we say, okay, we have an isActive Boolean. If each scan code in the current key event is pressed, then this isActive variable will remain true. Otherwise, if that key is not pressed, then we're going to set isActive to false. And then if all the keys, if we made it all the way down here and all the keys are active, then we're just going to call the callback function. Here in update events, we're just going to iterate through any events that are registered. And if that event is the current event that was just triggered, such as SDL quit, then we're going to call the callback function. And then we have functions to register events as well as key events. Okay, so now that everything is working properly and all of my systems are registered, we can go ahead and run the debugger and I can demonstrate everything working. So you can see right now we've got a black screen. That is just the render clear color. We could update and just make it something, just add random values here. And now you see the background color should be different, whatever that value is. The sort of green color. Now you can see pressing the X will trigger an SDL quit event. There you go. I can also press CTRL+W to quit out of the window, or I can do Alt F4. And then I can even do that with the other CTRL+W or Alt F4 on the other side of the keyboard, and that still works. Right now, nothing really exciting is happening. To me, it's really exciting that the events are working and that the window manager is working properly. But from an actual gameplay standpoint, we haven't really done anything fancy yet. In the next video, I'm going to try to make a player object and render that to the screen and get it to move around. And hopefully we can even make a camera object to follow the player so that we're not just stuck to a 640 by 480 screen. Thanks for watching. I'll see you next time.